This is it, folks. Unit 8, Preview Video 8.7, Volume of Spheres, your last preview note of the year. Sit tall, pull your shoulders back, and inhale. Hold your breath. Birthday candle, very slow. Don't forget the date, time, and location, and a parent's sign-off. We're going to be talking about two distinct things here, surface area and volume. Surface area and volume. Surface area and volume of spheres, specifically. But first we're going to talk about what is the difference between volume and surface area. If you have a gift here, surface area would be the area of the wrapping paper. If you were to unfold it, it'd be the area of the wrapping paper. It measures the outside area of the solid, the area of the surface of the solid. Volume would be like what the gift is on the inside. We've been focused exclusively on volume for the past 3 lessons. Just as a recap, one dimension is strictly length. So this edge right here, if I were to measure that edge, that is one dimension because it's just length. 2 dimensions would be as if this object has wrapping paper and you unfold the wrapping paper and you find the area. That is a 2-dimensional concept. That is length. Technically, we call it length and width. Volume, of course, is 3 dimensions, length, width, and height. In the next couple minutes, what we're going to be learning is how to take 3-dimensional objects and draw its 2-dimensional surface areas. These are called nets. So imagine this solid is covered precisely in paper. You were able to slice the edge off the paper and unfold it. What would that net look like? Now, there's more than one way to draw it. Okay, so that's very important. You need to know there's more than one way to draw these. But so you just go through the physical act of one piece at a time, especially how it's connected. So, for example, if I were to start with the base, and I'm going to draw just that. And we're drawing it as if it's a flat piece of paper. And I'm going to get my dimensions on there, which I have. That's 13. My apothem at a right angle is 8.9. Now, I have these rectangles, and there's 5 of them. So I'm going to draw those rectangles as if they're the flaps. 5 of them. And I do want you to pull over the dimensions. Not only are you drawing, but you are visualizing where those dimensions are. So for example, this is 13, and then this edge length would be 7 on all of them. Then you have a bottom pentagon, and if the idea of a net is you have to keep it connected. So it's connected to one of the flaps. It doesn't matter which one. So I'm just going to draw it like this. There's my one. Again, that's 13. And my apothem, 8.9. So you take the solid 3D and you unfold it in a 2D flat net. Now, cones are a little bit harder to see. Okay, obviously we have a singular circular base. Now, this will be easier when I demonstrate it in class. But this, if you were to slice this cone down the edge and unfold it, what you're going to get is something that looks like this, attached. So it doesn't really matter where you attach it, kind of at the edge. It's not exactly a triangle because when you wrap it around, it's not a triangle. It's more like a sector area. So that would be the net of a cone. Because if you were to fold those edges around and then connect the seam along this edge, you would get a cone. Then you have to be able to do this. You have to take a net, and what I recommend is you put your hands in front of you and physically imagine that piece of paper in your hands and go through the motions of folding it back into a solid, like literally go through the motions. If you were to go through the motions and you take each of these points and fold it back into a vertex, you would see that you have a hexagonal pyramid. If you were to take all those corners and fold them, so go through the motion of physically folding this back into a solid. And you're like, what's that? If you fold the two circles down and you wrap that label around, you should be able to see what we have here is a cylinder. With the label rectangle connecting. Now let me draw it to scale. It's more like a squatty cylinder. So you have to go from 3D into 2D and 2D into 3D. You do this page, fold these back into a solid and draw. Pause the video. Welcome back. Hopefully you're not copying. I really hope you took the time to do this on your own. So this first one was a cone. This was a triangular based prism. Oh, let's get the dimensions. You should have gotten the dimensions on here. Here, my diameter is 10. My slant height is 16.8. Here, this edge is, if I drew it that way, is 11, 8, and 11 again. Height is 14. If you did not do that, you should go back. This, you have a square base. Square base pyramid, and that 27 is a slant height. It is not the true height. The way it folds up, that's a 24. And that would be 19 and 19. Okay, so surface area, you need to be able to go 2D, 3D, 3D, 2D. Surface area is like wrapping paper. Our very last solid that we're going to deal with is a sphere. I love spheres. 3 reasons why I love spheres. It's easy to draw a sphere. There's no what's called lateral area. You don't have to distinguish between total surface area and lateral area. There's only one surface area. And you only need one singular dimension to find surface area or volume in a sphere, and that's radius. So it's easy to draw. The way you draw a sphere, this tennis ball, so you would simply draw a circle, and then you loop around basically what we considered an equator. Solid on one side, dotted towards the back to represent 3D. That would be the center of your sphere. We don't call it a midpoint because it's not a singular point on a segment. We call it the center. And then there would be your radius. Your radius would go to the edge like that. Technically, your radius also goes to the physical edge. You have to think of it in 3D in all directions. But that would be your radius. Now, those of you in art class, you would also, if it's a sphere, you'd be doing this lovely shading stuff, and that's just wonderful. But in geometry class, we're not going to worry about the fancy shading. So area of a sphere is like the wrapping paper, and I have a demonstration of what does area of a sphere actually look like. So when you unwrap the wrapping paper, the GIF is redistributing the area to turn the area into a rectangle. And the height of that rectangle is twice of the radius. And the length of that rectangle is 2 pi r because it's along the circumference. So the surface area of a sphere is going to be this length, 2 pi r, times this width, 2 radius. So 2 pi r times 2r is going to be 4 pi r squared. So the surface area of a sphere, which would be like the felt of this tennis ball, is 4 pi r squared. You only square the radius there. Volume is a three-dimensional concept. It's like the gift inside. Now, I don't have an illustration for volume. It's a little bit more complicated. It starts the same way, though, 4 pi r. But the difference you need to know here, area is 2 dimensions. Volume is 3, so that's going to be r cubed, but the whole thing's over 3. So surface area, 4 pi r squared. Volume, 4 pi r cubed over 3. We're going to do just a couple quick problems together. Put your finger right here with me, right there. I like you to read this out loud. Follow the red dot. Read out loud. Finger on the paper. Go. Let's start by writing our equations. So when we come here, surface area is going to be 4 pi r squared. So it's going to be 4 pi 8 times 8. So that's basically going to be 64 times 4. Try to avoid calculators for single-digit multiplication. Exercise that third grade math. 6 times 4 is 24, so that's 5, so that's going to be 256. So our surface area here is going to be 256 pi inches squared. That's exact terms. Approximate terms, 804.2-ish inches squared. Exact terms is always preferred, unless you have to do something else with it. So 8 times 8 times 8, that's basically 64 times 8. And then we're going to do times 4. So we get 2048 pi over 3. That's exact terms because 3 does not go into 2048. So to get the approximate form, of course, $21,144.7 inches cubed. Volume, surface area. Ready? Put your finger right here. Finger on the paper, folks. Read out loud. The volume is 972 pi meters cubed. Find the surface area. Remember, the only thing you need for surface area and volume of a, I just said cube, sphere, is a radius. That's the only thing you need. Always start with what you have. The volume is 972 pi meters cubed. We want the surface area. Surface area is going to be 4 pi r squared. What do I know about volume? I know volume for a sphere is 4 pi r cubed over 3. And that's going to equal 972 pi over 972 pi. Basically, you cross multiply. So I'm going to get 3 parentheses 972 pi equals 4 pi r cubed. You're like, Miss Way, why didn't you multiply? The key to multiplying is not multiplying, it's factoring. So I'm going to factor out the 4 and the pi. That cancels. This cancels. 972 is divisible by 4. I get 243. So 3 times 243, now that I've canceled, you're going to get 729. You're like, how do I do a cubed root? Okay, in all honesty, you guess and check. Cube roots. Now you get some markers here. 5 cubed, you should know what that is. 5 times 5, 5 times 5 times 5 is 625. So we are just above 625. So you should know that 10 cubed is 1,000 and 5 cubed is 625. So obviously this is right above 625. So let's try 7. Let's try 8. There you go. And then 9. We got 729. So our radius here, cubed root, so you draw it like this with a little 3, cubed root, r is 9. Now we just come down here, and we have 9 squared, 4 pi. That's going to be 81 times 4. Ta-da! Your surface area is 324 pi. What were your units? Meters. Squared. Now, because I did not, give me just a second, because we didn't do corrections here, what I want you to do is 3 bullets. What do you want to remember? I'm going to be looking for those 3 bullets. Make sure you write 3 bullets right there.